James Hopwood JeansThe, Mathematical Theory of Electricity and Magnetism. All books on my channel are in public domain. Subsequent sections of the books are organized in playlists. Links provided in the last minute of the recording. Please subscribe, like and comment. Please be mindful that this book was printed in 1907. Conceptions and units might be incompatible with the modern ones. Chapter 2. The Electrostatic Fields of Force. Conceptions used in the survey of the fields of force. 1. The intensity at a point. 30. The space in the neighborhood of charges of electricity, considered with reference to the electric phenomena occurring in this space, is spoken of as the electric field. A new charge of electricity, placed at any point O in an electric field, will experience attractions or repulsions from all the charges in the field. The introduction of a new charge will in general disturb the arrangement of the charges on all the conductors in the field by a process of induction. If, however, the new charge is supposed to be infinitesimal, the effects of induction will be negligible, so that the forces acting on the new charge may be supposed to arise from the charges of the original field. Let us suppose that we introduce an infinitesimal charge epsilon on an infinitely small conductor. Any charge E1 in the field at a distance, R1 from the point O, will repel the charge with a force epsilon, E1 over R squared. The charge epsilon will experience a similar repulsion from every charge in the field, so that each repulsion will be proportional to epsilon. The resultant of these forces, obtained by the usual rules for the composition of forces, will be a force proportional to epsilon, say a force, R epsilon in some direction OP. We define the electric intensity at O to be a force of which the magnitude is R, and the direction is OP. Thus, the electric intensity at any point is given, in magnitude and direction, by the force per unit charge which would act on a charged particle placed at this point. The charge on the particle being supposed so small that the distribution of electricity on the conductors in the field is not affected by its presence. The electric intensity at O, defined in this way, depends only on the permanent field of force, and has nothing to do with the charge, or the size, or even the existence of the small conductor which has been used to explain the meaning of the electric intensity. There will be a definite intensity at every point of the electric field, quite independently of the presence of small charged bodies. A small charged body might, however, conveniently be used for exploring the electric field and determining experimentally the direction of the electric intensity at any point in the field. For if we suppose the body carrying a charge epsilon to be held by an insulating thread, both the body and thread being so light that their weights may be neglected, then clearly all the forces acting on the charged body may be reduced to two. A force R epsilon in the direction of the electric intensity at the point occupied by epsilon. The tension of the thread acting along the thread. For equilibrium, these two forces must be equal and opposite. Hence the direction of the intensity at the point occupied by the small charged body is obtained at once by producing the direction of the thread through the charged body. And if we tie the other end of the thread to a delicate spring balance, we can measure the tension of the spring, and since this is numerically equal to R epsilon, we should be able to determine R if epsilon were known. We might in this way determine the magnitude and direction of the electric intensity at any point in the field. In a similar way, a float at the end of a fishing line might be used to determine the strength and direction of the current at any point on a small lake. And, just as with the electric intensity, we should only get the true direction of the current by supposing the float to be of infinitesimal size. We could not imagine the direction of the current obtained by anchoring a battleship in the lake, because the presence of the ship would disturb the whole system of currents. Lines of force. 31. Let us start at any point O in the electric field, and move a short distance OP, in the direction of the electric intensity at O. Starting from P, let us move a short distance PQ in the direction of the intensity at P, and so on. In this way we obtain a broken path OPQR, formed of a number of small rectilinear elements. Let us now pass to the limiting case in which each of the elements OP, PQ, QR, is infinitely small. The broken path becomes a continuous curve, and it has the property that at every point on it the electric intensity is in the direction of the tangent to the curve at that point. Such a curve is called a line of force. We may therefore define a line of force as follows. A line of force is a curve in the electric field, such that the tangent at every point is in the direction of the electric intensity at that point. If we suppose the motion of a charged particle to be so much retarded by frictional resistance that it cannot acquire any appreciable momentum, then a charged particle set free in the electric field would trace out a line of force. In the same way, we should have lines of current on the surface of a lake, such that the tangent to a line of current at any point coincided with the direction of the current. And a small float set free on the lake would describe a current line. 32. The resultant of a number of known forces has a definite direction, so that there is a single direction for the electric intensity at every point of the field. It follows that two lines of force can never intersect. For if they did, there would be two directions for the electric intensity at the point of intersection, namely, the two tangents to the lines of force at this point, so that the resultant of a number of known forces would be acting in two directions at once. An exception occurs, as we shall see, when the resultant intensity vanishes at any point. The intensity, R, may be regarded as compounded of three components x, y, z, parallel to three rectangular axes O, x, O, y, O, z. The magnitude of the electric intensity is then given by R squared equals x squared plus y squared plus z squared, and the direction cosines of its direction are x over r, y over r, and z over r. These, therefore, are also the direction cosines of the tangent at x, y, z to the line of force through the point. The differential equation of the system of lines of force is accordingly dx over x equals dy over y equals dz over z.